Welcome to this video concluding some of the notes and example problems for the second half of the Techniques of Differentiation section of your binder. I'm going to go through some of these problems. I know I went through some of them in class. I'm going to go through some other ones here. This will hopefully help you conclude your homework assignment that I have in the homework section. So right now I am on page 35 and I'm looking at part 8, or question 8 if you will. And we're talking about finding an equation of a tangent line at a point. So let's look at question C. So I've got a function f of x equals 8 over x minus 8x squared at negative 2, negative 6. And as we talked about in class, when you want to write an equation of a line, you need a couple things. You need a slope and you need a point, right? We can use that good old point-slope formula, which I'll write here again, y minus y1 equals mx minus x1. Where am I going to get that slope? I'm going to get it at the derivative of x1. Okay. So first things first, I need to take the derivative of that function, and I need to evaluate it at negative 2. As we've done before, when we have variables in our denominator, we are definitely going to want to rewrite this using negative exponents. So instead of saying 8 over x, we'll say 8x to the minus first minus 8x to the minus 2. We'll take our derivative. That's going to get us negative 8x to the minus 2 plus 16x to the minus 3. And then we can get rid of those negative exponents again by putting them in the denominator. Negative 8 over x squared plus 16 over x cubed. Okay, next step is to get the specific slope at negative 2. So I'm going to plug in negative 2 into both of these. So negative 2 squared is 4. And negative 2 cubed is negative 8. So from there I get negative 2 minus 2, which will be negative 4. So that's my slope. So to get my tangent line, I'm just going to plug this point, negative 2, negative 6, and that slope, negative 4, into my point-slope form. So I'll get y plus 6, because the double negative, equals negative 4x plus 2. And you can do the algebra and put that in slope-intercept form if you like, and you get y equals negative 4x minus 14. Okay, let's do the same thing with question D. So same idea. Now we're going to take the derivative of this function, but it's a quotient, so it's going to be a little more tedious, my derivative, but I'll use my quotient rule. So f prime of x is going to be, all right, low, d high. Well, d high, since this is a nice linear function, is 1. So I'm just going to do x squared plus 4 minus high d low. Okay, well, the derivative of x squared plus 4 is 2x, and I'm going to distribute the negative 2x into x minus 4, and I'm going to do that over the bottom squared. Square the bottom, and away we go. So x squared plus 4, all of that squared. Okay, and I can just clean up the numerator a little bit. So I'll distribute my minus 2x. I get minus 2x squared plus 8. So when I combine like terms, I get negative x squared, plus 8x, and then plus 4, all over x squared plus 4 squared. Now at this point, I wouldn't want to do any more simplifying or expanding, particularly with the denominator, because the next step is going to be to evaluate the derivative at 2, and I can do that right from this stage of the game. So we'll say that f prime of 2 is going to be okay. So I do 2 squared is 4, but I put a negative sign in front of it. 8 times 2 is 16 plus 4, all over 8 squared. So then I get 16 over 64, which I can reduce to be 1/4. I could take a 16 out of both of those. Okay, let me just add another page here because I'm running a little bit low of space. So we know that the slope of the tangent line from the last page was 1/4. And the point that we're using is 2 comma negative 1/4. So we're just writing the equation of a line with that slope that goes through the given point to 1/4. So we have y plus 1/4 equals 1/4 x minus 2. We'll distribute the 1/4 in. We'll bring the 1/4 from the left over, and in slope-intercept form, the tangent line through the function x minus 4 over x squared plus 4 at 2 comma negative 1/4 is going to have an equation of y equals 1/4 x minus 3/4. So that's tangent lines. Let's take a look at another set of questions. Let's look at a normal line. Okay, as we talked about in class already, a normal line is a line that's perpendicular. So we have to use the idea of what we know about perpendicular lines. We know they have slopes that are opposite reciprocals of each other. So what we mean is basically perpendicular to the tangent. So we're going to find the slope of the tangent like we did in the last example. Then we're going to flip it and change its sign, and that's going to be our slope that we use for the line equation. So let's look at question B. So we want to get the normal to the graph of f at the point 4, negative 2. So let's take our derivative of minus 6 over root x plus 1. Okay, I got to use my quotient rule. So when we do our low d high, notice what happens. Low is root x plus 1. D high is 0. That's going to zero out. So I don't even need to write that. All I really need to do is negative high d low, because that's the only part of the quotient rule that's going to have any value. So minus high, negative 6, d low, which will be 1 over 2 root x. Square root of x, you should have that derivative memorized. It's 1 over 2 root x. All over the bottom squared, root x plus 1 squared. We can simplify the top a little bit. The double negative becomes a plus, so I believe we get 3 over the square root x all over square root of x plus 1 quantity squared. Again, don't need to clean it up much more because the next step is going to be to evaluate this at 4. So I'm going to get 3 over root 4 all over root 4 plus 1 quantity squared. So that'll be 3 over 2 all over 9. And then that's going to reduce, if I multiply by the reciprocal of 9, to 1/6. So that's the slope of the tangent at 4. The slope of the normal is going to be the opposite reciprocal, which is negative 6. So I'm going to plug negative 6 and the point 4 comma negative 2 into my line equation. I get y plus 2 equals negative 6x minus 4. So y is going to equal negative 6x minus 22. That's going to be, plus 22. That's going to be the normal line. Now let's talk about horizontal tangents. So as we said before, if we're talking about a tangent line that's horizontal, well, what's the slope of a horizontal line? Slope of a horizontal line is 0. So essentially, we are basically taking the derivative, setting it equal to 0, and figuring out at what points the derivative is going to be 0 on this curve. So we'll start out with b, a nice polynomial. The derivative of that is going to be, with our power rule, 4x cubed minus 8x. We'll set that equal to 0. We get 4x cubed minus 8x equals 0. We could take out a GCF. So we could take out a GCF of 4x, and we're left with x squared minus 2. We'll set each of these equal to 0. So I know if 4x equals 0, that means x has to equal 0. If x squared minus 2 equals 0, x has to be either positive or negative root 2. Remember, you need two answers. It's a quadratic. So you'll get x squared has to equal 2. So x can be either the positive root of 2 or the negative root of 2. Now all that's left to do is we're just going to take these three x values, plug them into the function, and that's going to get our points. You have to be very careful about what they ask for in questions. When I say a point, that means I need the x and the y. If I just said determine the x coordinates, I'm done. That's where reading the problem is going to be very important. Okay, so I still need the actual points, so I'm going to plug all these x coordinates into the function. Well, I hope that everybody can see with mental math that when x is 0, y has got to be 0. So the origin is going to be a point where we have a horizontal tangent for this curve. If we make x positive root 2, and actually if we make x negative root 2 as well, since this is an even function, we're going to get the same y value. So root 2 to the 4th is the same thing as negative root 2 to the 4th, and that is going to be 4. Root 2 squared will be 8, root 2 squared will be 2 times 4 is negative 8. So I believe at both positive root 2 and negative root 2, we're going to be at negative 4. Okay, because for both of these, we do root 2 to the 4th minus 4 root 2 squared. And that would get us, like I said, 4 minus 8, which would be negative 4. Okay? Let's look at part D. Okay, so I have a quotient rule again, so let's try it. The derivative of that function. Low, d high. Well, d high is 1, so low would just be x squared plus 3 times the 1. Minus high, d low. Well, the derivative of the denominator is 2x. And we're going to multiply that by the numerator, x minus 1. And we'll put all that over x squared plus 3, but this time we square it. Okay, we'll clean up the top. So we'll distribute that minus 2x in, and we get negative 2x squared plus 2x. So when we combine like terms, we get negative x squared plus 2x plus 3, all over the quantity of x squared plus 3, quantity squared. Okay, so I don't really care so much, again, about squaring out that denominator, because if it's a fraction, the only way the fraction is going to have a value of 0 is if the numerator is 0. So I really only have to set the top equal to 0. Plus 2x plus 3. Okay, so I'll take out that negative sign, and then that's like factoring x squared minus 2x minus 3. So that'll be at x minus 3 and x plus 1. So x can be 3, x can be negative 1. I'm going to evaluate those. I'll just give you the values to save some time. You can check me on the arithmetic. When x is 3, I got 1/6 for my y. And when x was negative 1, I got negative 1/2. So at those 2 points, we're going to have a horizontal tangent line for that given function. Now let's look at a table of values. This is something that, if I were a betting man, this is going to show up on the AP exam somewhere. You're going to get a table of values and be asked to do stuff with it, be it as a multiple choice question, be it as a free response question. In fact, as I said in class, this was the basis, a table of values was a basis of one of the free response questions on the 2016 AP exam. So it would make good sense for us to do as many forms of these types of questions throughout the course of this year as possible. So I don't have a function so much. I just have a couple function values. I know that g of 3 is 4, g prime of 3 is negative 2, h of 3 is 3, and h prime of 3 is pi. So the whole point of this is to see, do you understand the rules without me giving you an actual function? So we'll do a couple of these. So if we look at part A, I've got f of x is defined to be 4 times g of x minus 1/2 h of x plus 1. So this is testing, do you remember how the constant rule works? If you multiply a function by a constant and take its derivative, it's just the derivative times the constant. So what we mean by that is the derivative of f now will be 4g prime of x plus 1/2 h prime of x, and then the derivative of 1 is 0, so we would stop there. Okay, so I want f prime of 3, so I make all those x's 3, and then I go to my chart. So 4g prime 3 plus 1/2 h prime 3. All right, g prime of 3 is negative 2, so that will become negative 8 in my first term. H prime of 3 is pi, so that'll become pi over 2. And that's the derivative of f at 3. Just by using all of our properties of derivatives. Okay, let's look at letter B. Letter B is a typo. The function that I really want to do is I want to do f of x is defined as g of x, h of x. So it's a product. So it's basically asking you, do you know the product rule? So we'll take the derivative of f. That's just going to be kind of the crisscross of derivatives. So g prime h plus h prime g. I'm running out of room there. So when we evaluate this at 3, we're going to do the derivative of g at 3 times h at 3 plus the derivative of h at 3 times g at 3. Okay, g prime of 3 is negative 2, h of 3 is 3, h prime is pi, g of 3 is 4, so the derivative at 3 of this new function x would be negative 6 plus 4 pi. Okay, and we can stop there. And again, leave it in terms of pi. You don't need to do anything with 3.14 because we're assuming no calculator for any of these questions unless I say otherwise. So we want to leave it in terms of pi. Let's take a look at C now. So we've got f of x equals g of x over h of x. All right, well this one now is a quotient rule. But what I'm actually going to do to make my life easier for my quotient rule is I'm going to pull the 1/2 out and think of this as 1/2 times g of x over h of x. Because then I could just do the derivative of g over h and do half of that. So the derivative of that would be 1/2 low d high minus high d low. And then we'll square the bottom, and away we go. So f prime at 3 will be 1/2 h of 3, which is 3, times g prime of 3, which is -2, minus g of 3, which is 4, times h prime of 3, which is pi, all over h of 3 squared, which would be 9. Okay, that'll be 1/2 -6 minus 4 pi all over 9. We can reduce the 2's on top, and we'll get -3 minus 2 pi all over 9. Okay, so the last little piece of this chapter in the notes is talking about this idea of the second derivative of a function. And it is just the derivative of the derivative. We can take what are known as higher derivatives of a function by just repeating all of the differentiation techniques that we've already uncovered. And that'll get us the second derivative. If you take the derivative of that, you'd get the third derivative. If you take the derivative of the third derivative, you get the fourth derivative, and so on and so forth. Those higher derivatives will have different geometric interpretations, physical interpretations, and whatnot, and we'll uncover those later on in the course. Basically, if you're thinking about it in terms of slopes, the first derivative is the slope at a given point. The second derivative would basically be the rate at which the slope is changing at that point. For physics people, you might understand that idea a little bit, especially when you talk about motion. We're basically thinking of the idea of acceleration. That's what a second derivative would mean in the physical world, but it has a lot of other applications throughout the real world and throughout different scientific and real-world fields. We'll talk more about that later on in the course. For right now, I just want to do the mechanics, and I also want to show you right here in this table some of the notation. So basically, how we put that little prime for f prime of x to mean the first derivative. Well, if we put 2 of those little apostrophes, double prime, that means the second derivative. 3 would mean the third derivative. Beyond that, it gets a little bit hard to count. So what we do for fourth derivatives and beyond is we just put a little number in parentheses above the f to show that it's not a power, it's that number's derivative. So we'd say something like, if we wanted to take, I don't know, for some reason, the sixth derivative, we would say f with a little 6 in parentheses of x. That would notate to a reader that's the sixth derivative of f of x. Okay? So that's how we would do it when we're dealing with the prime notation. Same thing if it was y equals, if you do y prime, y double prime, y triple prime, so on and so forth. If you use the dy dx, this is a little bit weird. So same thing, you kind of look at like an exponent. You put, in the numerator, you put the order of the derivative as a superscript for the d. For the denominator, you do it for the superscript of the x. So d squared y over dx squared, d cubed y over dx cubed, second derivative, third derivative, and so on and so forth. Okay, so let's do a couple of these, and let's really pay attention to both the mechanics and the notation. So nice polynomial, we can take repeated derivatives of that in our sleep. We're just using the power rule a million times. So the first derivative, I hope everybody can do that one relatively quick. 3 times 8/3 is 8, drop a power, we get x squared. 5 times 2 is 10, drop a power, we get x. 7 times 1 is 7, drop a power, we have no x anymore, so it's just going to be minus 7. When we take the second derivative, we do the power rule yet again. 2 times 8 is 16, drop a power, we get x. 1 times -10 is -10, drop a power, so it's just minus 10. And the -7 is a constant, so its derivative is 0. Okay? We look at letter B. Okay, I've got a polynomial over a monomial here, so I don't want to waste my time and use the quotient rule. Instead, I want to just simplify. X plus 4 minus 2x to the negative first. Now I will take my power rule and take my first derivative, so the derivative of x is 1, the derivative of 4 is 0. When I do minus 2x to the negative first, negative 1 times negative 2 is 2. Drop a degree, we get x to the minus 2. I'm not going to put this in fractional, or put the negative in a denominator yet, because I want to find the second derivative, so it's much easier to keep it in negative exponential form, because I can redo my power rule. So the derivative of 1 is 0. The derivative of 2x to the minus 2 would be negative 4x to the minus 3. So the second derivative of that function is negative 4 over x cubed. Okay? Notice with polynomials, at least, the more and more you differentiate, the less and less complicated it gets. And in fact, with polynomials, what will eventually happen is you'll zero out. You'll get to a point where all your powers of x drop out, and you're left with a constant. Then when you take that derivative, you have the derivative of 0. Now, when you have things like fractional exponents, like in C, or you have a quotient like in D, that's not going to happen. It's not going to quote-unquote zero out. So like, let's look at question C. So we've got y equals 4 root x minus 2 over root x. All right, for starters, I'm going to rewrite that as fractional exponents. So 4x to the minus 2 minus 2x to the minus 1/2. So I'll take my derivative. Let's use the other notation, dy dx, just so you can get the idea of how we would write that. Half of 4 is 2. 1/2 minus 1 is negative 1/2. Negative 1/2 times negative 2 is going to be positive 1. Negative 1/2 minus 1 is negative 3/2. Again, don't want to fix the negative exponents. Don't want to fix the fractional exponents, because I'm doing the derivative again. So the second derivative, so d squared y over dx squared, would get us negative x to the negative 3/2 minus 3 over 2 x to the minus 5/2. Now would be a good time to fix my negative exponents since I'm done. So I get negative 1 over x to the 3/2 minus 3 over 2x to the negative 5/2. Okay? Let's look at the last one. I'm a little bit out of space, so I'm going to do this on a blank page. So we had f of x equals x over x minus 1, and we want the second derivative of that function. Now, we can't go from the function to the second derivative. That's one other thing you got to realize. There's no shortcut there. You got to get to the second derivative by taking the first derivative. So, we'll take the first derivative. I have to use the quotient rule because I have a polynomial denominator. So, here we go. We'll do low, d high, derivative of x is 1, low is x minus 1, minus high, d low, so x times 1, all over the bottom squared. All right, we'll clean this up. We get x minus 1 minus x, all over x minus 1 quantity squared. So when we clean up the numerator, all we're left with is negative 1. This time I am going to expand because I'm going to take the derivative again. So I'm going to make this denominator x squared minus 2x plus 1. Okay, square the first, double the product, square the second. Now I'm going to differentiate negative 1 over x squared minus 2x plus 1. And again, got to use my quotient rule. There will be shortcuts to this. We're going to do that in the next section. Right now, you got to use the quotient rule. So low d high. Well, my high function's a constant, so d high is 0. So I can kind of skip the low d high part, and I can just do minus high d low. So minus negative 1 times the derivative of the bottom, which is 2x minus 2. Then I can square the bottom. And I'm going to write it as x minus 1 to the 4th, and you're going to see why I did that in just a second. All right, when I multiply out the numerator, I get 2x minus 2 all over x minus 1 to the 4th, which we can actually simplify more, because notice 2x and negative 2 have a GCF of 2, and I'm left with x minus 1. Also notice that I have 4 copies of x minus 1 in my denominator. So I can take one of those out of the denominator and cancel out the x minus 1 in the numerator, and I am now left with my second derivative as 2 over the quantity of x minus 1 to the third. Okay? I know this is a little bit of a longer than normal video, but I hope this gives you a little bit of examples so that you can tackle the rest of that homework section in this chapter. So what I'm expecting is for you to finish all the homework problems on page 39 and page 40 in your notebook. Okay? If you have any questions, feel free to ask me. Otherwise, I will see you back in class. Thanks again for watching.